Okay, we're picking up where we left off in the last section of chapter 2, talking about the derivative as a function. So what we talked about at the start of this section is if we've got some function, f of x, we can think about the idea of what is the derivative of the function f, or the function f of x, the general derivative of this function, this expression of x. Let's say this is the square root of x. And what this means is that we're just going to take the function expression and plug it directly in, leave it in general terms of x and plug it directly into the limit definition of the derivative. Any form of the limit definition of the derivative, it doesn't matter, right? So the limit as the denominator of the difference quotient, to where the difference quotient can be in any form you want, doesn't matter. The limit as the denominator of the difference quotient approaches 0. That's the derivative. So you plug the function into the limit definition of the derivative, evaluate the limit, and you get some new expression of x that you call the derivative of the original function of x. You call it f prime of x. And we worked an example in the previous video where we plugged this into the definition of the derivative and got that f prime of x in this case is 1 over 2 root x. Okay, and so what they're talking about next here is some other notations that you can use to indicate the derivative of a function. So if we use the traditional y is equal to f of x to indicate that the independent variable is x and the dependent variable is y, then some common alternative notations for the derivative are as follows. So, okay, the dependent variable is y, and y is some function of x. So you can state the derivative of this function as f prime of x. You could state it as y prime. You could state it as dy dx, or df dx, or dx f of x. You could use this capital D f of x. Any of these notations here are acceptable to indicate the derivative of some function, right? And in all of these cases here, we first have to state, okay, look, here's this function y is a function of x, and here's the function. So with this established, all of these forms here, these notations here, are indicating the derivative of this function. Y, it's a y prime, f prime of x, capital D f of x, right? These are all indicating the derivative of f of x. Now it says that the symbols capital D and this d over dx are called differentiation operators because they indicate the operation of differentiation, which is the process of calculating a derivative. So yeah, they're saying that it's really clear with this notation here and this notation here that you've got some operator acting on the function, right? The differentiation operator acting on the function f of x, the differentiation operator acting on the function f of x. And what they mean by operator, when they say an operator, so, okay, a function takes in an input, a real number input, and outputs a real number, right? I mean, in complete general, you can input a vector of real numbers, like 3 real numbers, 4 real numbers, whatever. You can input a vector of real numbers into a function and then get out a vector of real numbers. Like we talked about it in algebra, you could have a function or a relation. Maybe it's not a function, so maybe you've got certain, one input mapping to more than one output. But a function or a relation, you can input something like so the inputs would be into the function or relation would be, I guess this would be a function, the weight of a package and the volume of a package. And then the outputs would be the cost to ship and the time to ship. So in that case, that would be a function. You're not going to have the same input mapping to more than one outputs. That wouldn't make any sense. But you see, that would be a vector. You have a 2-dimensional vector input and a 2-dimensional vector output. You're inputting real numbers and you're outputting real numbers. Okay, an operator in math is when you're inputting a function into the operator, and then you're you're getting as an output a function, right? That's exactly what the differentiation does, the differentiation operator, where we inputted this function square root of x into the differentiation operator, and we got out a function. Then it's the same idea. In general, you can input a vector of functions into the differentiation operator and then get out a vector of function. Okay, but now it's only pointing out that it's saying that this capital D f of x, that this is a differentiation operator, and so is this. So it's almost like it's suggesting that these other forms aren't differentiation operators, but that's not true. It's just that these two forms are the most explicit, because we can take any, we could put D, capital D, and then put the function, right? D square root of x. This is the differentiation operator applied to the square root of x. Or dx square root of x. This is the differentiation operator applied to the square root of x. But we could do this with any of these forms. So that the y prime here, you would do, there you go. This is the differentiation operator applied to the square root of x. Or this, the dy over dx or df over dx, you do d, right? Once again, this is just applying the differentiation operator to the square root of x. Okay, now, the symbol dy over dx, which was introduced by Leibniz, Wilhelm Gottfried Leibniz, should not be regarded as a ratio for the time being. It is simply a synonym for f prime of x. Nonetheless, it is a very useful and suggestive notation, especially when used in conjunction with increment notation. Okay, so yeah, this dy over dx is called Leibniz notation, and we're going to become very familiar with this notation as we progress in the course, and then even in differential equations, you really make use of this form of the notation for the derivative. And what's useful about this notation is, like it says, it's very suggestive. It's very illustrative of the meaning of the derivative. The derivative is a ratio. Any derivative whatsoever, it doesn't matter what the form is, however you derive the definition of the derivative, no matter what, like we've talked about, no matter what, in all circumstances, it always comes down to, you're going to have some function, then you'll have a point P on that function, your point of interest. Then you construct the difference quotient of the function f of x with respect to point P, in which case the difference quotient is just the slope of the line between point P and some point Q that's off of point P. Where exactly point Q is, it can vary. It's a variable location as long as point Q is not on point P. That's the difference quotient of the function f of x with respect to point P. Then you just take the limit as Q approaches P of that difference quotient. So what that means is that every single derivative in all circumstances is fundamentally the slope of a line. So what that means is that, so any slope of a line is a ratio, right? It's a delta y over delta x, a delta output over a delta input, which is exactly what this is showing, right? It's giving you a really good illustration of the derivative as a ratio, the fundamental meaning of what the derivative is. It's a delta y, they're calling this a dy over a dx. Okay, so, but now, what is this d here? Well, why not just call this, okay, delta y over delta x? Change in y over change in x. Well, the d notation is used to indicate that this isn't just any typical change in y or typical change in x. This is a special case of an infinitesimally small change in y and an infinitesimally small change in x. These are called infinitesimals. So like when you see a delta like this is referring to a finite change in y, a finite change in x. The temperature outside goes from 70 degrees Fahrenheit to 75. That's a delta T of 5 degrees Fahrenheit. When you see a d notation like this, a d variable, in certain circumstances that could be referring to a finite change, in which case these would be acting as differentials, which we're going to talk about that more later. But at the moment, when it comes to the perspective of the definition of the derivative, this Leibniz notation here, with any of these d's, when you see a d variable, dy, dx, that's in reference to a change in that variable, just like this is. But Specifically, it's referring to an infinitesimally small change. Okay, so, but how small is infinitesimally small? Well, you want to think about an infinitesimal, so infinity. When you ask the question, how large is infinity, that's the same idea as asking, how small is an infinitesimal change? And we know the answer to these questions from the precise definition of the limit. When someone asks you, how large is infinity, or how small is an infinitesimally small change, it's all about that infinitely powerful calculator idea. When it comes to the precise definition of the limit, how the limit as x approaches a of f of x is equal to L. Right? So how close does the input x get to a? We talk about x approaching a. Well, how close to a do we get? The answer is we prove that this limit exists and is equal to L from the perspective that you could have an infinitely powerful calculator and you could be a plus 0.000 a quintillion zeros 1. That would be the input into f of x, a plus 0.000 a quintillion zeros 1. And you're going to have something that's very close to L. You could specify however close you want the output to be within L, however many decimal places that you could possibly imagine. And there's going to be some band around A that you'll need to input into f of x that will allow you to be that close to L. And so as long as you have an infinitely powerful calculator that can handle this many decimal places, then you can do that. You can make that specification. And so with the limit definition of the derivative is a limit. So this is point A. This is f of A, point P. So if this is Q, well, when you take the limit as Q approaches point P, then the delta x is getting, so yeah, it's the limit as Q approaches point P from either side of P. The delta x is getting infinitesimally close to A from either side of A. So dx is 0.000 a quintillion zeros 1, but even smaller than that. But because y is a function of x, as Q approaches P, as delta x gets infinitesimally small, well, then so does delta y. These two are related. If you change delta x, then you're automatically changing delta y. So as delta x gets infinitesimally small, then delta y also gets infinitesimally small and turns into dy. Okay, so now a common question that's asked is, okay, well then is dy a number? Is dx a number? Is this a ratio? Because as we progress in the course, this gets really confusing. When we start looking at these variables here, these dy's and dx's as differentials, then from there, we start to, well, we'll have an equation like dy over dx is equal to the 1 over 2 root x. We'll multiply both sides of this equation by dx and get dy is equal to dx over 2 root x. You'll see examples of differential equations and these physics equations with derivatives where they're moving these differentials all over the place and then integrating both sides. And it's confusing because, well, okay, then that means that these must be numbers and this is an actual ratio. Okay, well, there's going to be a series of videos as we progress in the course that are going to talk about this whole idea of when you're allowed to treat dy and dx as a number, what exactly differentials mean, how you'll see professors manipulating equations with Leibniz notation like this, moving the dx and the dy around everywhere and then like integrating both sides, because we're going to see that these infinitesimals here, or you can sometimes call differentials, are part of the integration process, that they're part of integrals. So, okay, at the moment, in this video, all we're going to talk about, all we want to think about is the question of, okay, are these numbers? Is this a ratio? From a technical perspective, a true fundamental perspective, let's think about the idea of, is dy a number? Is dx a number? And is this a ratio? All right, so the question of, are dy and dx numbers? The answer to this question is, dy and dx are as much of a number as infinity is a number. So from a technical math perspective, mathematics says that infinity is not a number, which is kind of confusing because I mean, like technically it is a number though, right? When you say infinity, what does infinity mean? Infinity means it's an arbitrarily large number. So the definition of infinity has the word number in it. So it is a number. It really is. Infinity is a number. If my bank account is ballooning to infinity, if I told you that, if I said my bank account is just going to infinity right now, well, that means that I'm making a lot of money. The balance in my bank account is getting higher and higher and higher and higher. There's a number in my bank account that I'm referring to, an amount of money. But the idea is, though, when math says that infinity is not a number, they're just saying that you're really not being very specific at all. It's just an abstract term you're applying, as opposed to, so if I used the variable a, so here's the variable a, which we know that means that a can be any real number. It represents any real number. Well, in that case, you might say, well, this is the same idea then. Infinity is not a specific number, and a, you're not saying a specific number. However, there is a difference, though. We look at just the variable a, the algebra variable a. This is a number. This is a specific number. Because if you have like an algebraic equation, you can solve for a. A is one number. A represents one number. Infinity is this abstract idea. You don't solve for infinity. You see the difference, okay? And so it's the same idea when it comes to dy and dx. Dy and dx are coming from, infinitesimals are coming from this limiting process here. Q is getting infinitesimally close to p, so delta x is getting infinitesimally smaller and smaller and smaller. But that's not a specific number. That's not a variable. That's just an abstract concept that we're saying is called infinitesimally small. We're calling that an infinitesimal. So technically, the technical answer is that from a math perspective, dy and dx are not numbers in the sense that the variable b is a number, but they are numbers in some sense because, again, delta x or dx is some distance away from a. It's some number that's very close to a on either side of a. It's a number. Now, when we think about, okay, so is this a ratio? This can get confusing because, okay, if we have y is equal to the square root of x, okay, so dy over dx is 1 over 2 root x. All right, so when x is equal to 4, the input x is equal to 4, what's the derivative? Okay, well, square root of 4 is 2, it's 1/4. Well, look, there you go. dy over dx is equal to 1/4. That's definitive proof that dy over dx is a ratio. Well, in actuality, though, this is not the case. dy over dx is not a ratio. This is deceiving because if we think about this fundamentally, the meaning of the derivative, the definition of the derivative, this is a definition here. This, for y is equal to the square root of x, dy over dx is equal to 1/4. This is a definition. It's a definition in the sense that if we say the limit as x approaches a of f of x is equal to L, well, when we're actually looking at the mechanics of what's going on with the limit, we know that you're never actually plugging a into the function. And we're never actually settling in on L itself. It's a definition. We say that, okay, if the function has this behavior as x approaches a where it's like sandwiching or constraining around the output value L, then by definition, we're going to say that this limit is equal to L. But like if you're actually going through the mechanics with your calculator of the meaning of the limit, you're never actually equaling L. As opposed to if you plugged in, like, okay, so C over B. If C is equal to 8 and B is equal to 4, that is exactly equal to 2, right? C over B is a ratio. dy over dx is technically not a ratio. Okay, so that's an introduction to Leibniz notation. Again, we're really going to be coming back to this notation periodically throughout the rest of this course and differential equations. So there's a lot more for us to unpack about Leibniz notation. So the first topic we're starting with is just, okay, is this a ratio? Are these numbers? Okay, and so now it says that referring to equation 2.7.6, we can rewrite the definition of the derivative in Leibniz notation in the form. So you can apply Leibniz notation. So again, it does not matter whatsoever if you've got some function f of x, some function y is equal to f of x, and you want to find the derivative of this function, you can plug that function into absolutely any form of the definition of the derivative that you want. We've talked about 3 different forms of how you can set up the difference quotient, right? And then take the limit of that difference quotient, the limit as the denominator of the difference quotient approaches 0. You can plug y is equal to f of x into any of those forms, get the derivative, and you can state that derivative. So if this is square root of x, so you can plug this into any form you want and evaluate the limit, and you'll get, okay, as far as the notation that you use to say that this is the derivative of y or f of x, you can use any of these. You can say that this is dy over dx. That's fine. But what they're saying here is that Leibniz notation really matches up well, is really the most illustrative with this form of the definition of the derivative, the third form that we learned, right? So this was some function y is equal to f of x. You have point P. You call this x1, and then you call point Q being at x2. So this is f of x1 and f of x2. And so this is delta x, and this is delta y. So the difference quotient is just delta y over delta x. And so for the derivative, you take the limit as the denominator of the difference quotient approaches 0 of the difference quotient. And so what they're saying here is that, well, of all of these notations, the one that's most illustrative of that's like matches perfectly with this form here of the derivative is Leibniz notation. It's like a perfect marriage. It's not a requirement. I want to make that clear. It's not a requirement that Leibniz notation only applies to this form, but it's the perfect match. It's telling you, look, you have delta y divided by delta x, this difference quotient, this slope of the line between point P and some arbitrary point Q that can be located anywhere, some variable point Q that's just not on point P itself. When you take the limit as the delta x, the denominator of this difference quotient approaches 0. So this becomes infinitesimally small. Well, because y is a function of x, then that means delta y is going to shrink at the same time to some infinitesimally small change in y. And so what you're left with after performing the limit operation on the difference quotient, you're left with dy over dx, an infinitesimally small change in y over an infinitesimally small change in x. You see? Okay, so now it says if we want to indicate the value of a derivative, dy over dx, in Leibniz notation at a specific number a, we use the notation. So yeah, if you want to say, okay, the derivative of, so we had, it was y is equal to the square root of x. So earlier we looked at what was this derivative when x was equal to 4. Well, the correct notation would have been to specify it this way. So dy over dx evaluated at x is equal to 4. Or you can make it like a bracket. Either of these forms here. That just means that the bar here, or the bracket, means evaluated at. So dy over dx evaluated at x is equal to a. Okay. Now, let's talk about differentiability. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval from a to b, or an open interval from a to infinity, or from minus infinity to a, or from minus infinity to infinity, if it is differentiable at every number in the interval. Okay, so the idea of differentiability, if you're asked the question, you're given a function. You have some function f of x, and you're asking the question, where is f of x differentiable? And where is it not differentiable? The answer to this question is very simple. It's so if you draw the graph of f of x, you'll have the graph of f of x. Then, like we did in the previous video, you can draw the corresponding graph of f prime of x anywhere where f prime of x exists, where you plug a number into f prime of x and there's a point on the graph. Then the function is differentiable at that point. If there's no graph at some point on f prime of x, then the function is not differentiable at that point. And all this means is that when you go back to the limit definition of the derivative, it's anywhere where the limit exists. Any point where the limit exists and is equal to L. If that's the case, then on the derivative graph, there's going to be a point, an output point on the derivative graph, which means there's a derivative of the function at that point, which means the function is differentiable at that point. If the limit doesn't exist, then there's no derivative. So there's no point on the derivative graph. So the derivative doesn't exist. The function is not differentiable at that point. And it's all with respect to, so just like continuity, a function is continuous or not continuous at a specific point, right? That's a point-wise property. Well, the derivative, the precise fundamental definition of the derivative is it's a point-wise property. The derivative of a function is you're talking about specifically with respect to a single point at a time on a function. So when you're talking about differentiability, you're talking about a single point at a time. You have some function with its entire domain. You have a function in its domain. Then you can ask, okay, let's pick a single point in the domain of that function. And then you ask, is the function differentiable at that point? This is just like with continuity. You have a function and its entire domain. When it comes to continuity, you're asking, pick a single point in the domain. Is the function continuous at that point? Then you can ask the same question for another point and another point and another point. Same exact idea with differentiability. You're taking a function, picking a point within its domain, and asking, is the function differentiable at that point? Which just means that if you plugged that point in and that function into the definition of the derivative, does the limit exist? Does the derivative exist? If you inputted that point into the f prime of x, are you going to get a value out? If you do, it's differentiable. If you don't, it's not differentiable at that point. But now, as far as differentiability over an interval, well, this is the same idea as far as continuity over an interval. It's just saying that a function is continuous over an entire interval if for all points within that interval, the function is continuous. Well, it's the same idea with differentiability. Okay, but now note here, at the moment, it's only talking about differentiability over some open interval from A to B, or an open interval starting at A, then going off to infinity, or from infinity to the open interval at A. Why can't they say closed? Well, why can't a function, at least at the moment, why can't we think about a function being differentiable on some closed interval from A to B? So some closed interval from A to B. Why can't we think about a function, whether or not a function is differentiable over this closed interval? Well, because at the moment we've only talked about the general derivative as far as the limit as q approaches p from either side of p. So if we're excluding all of this portion of the function and trying to think about the derivative of this function f of x at a, well, we can't use the general definition of the derivative. We can't have point, if this is point P, this is our point of interest, point P at A, and so here's Q, well, we would have to construct the derivative as far as Q approaches P from the right, and we haven't talked about that yet. So we can't think about derivatives at endpoints at the moment. Okay. So where is the function f of x is equal to the absolute value of x differentiable? Let's think about for the entire domain of the absolute value function, which we know that you can input any number on the real number line into an absolute value. So its domain is negative infinity to infinity. For that entire domain, where is this function differentiable and where is it not differentiable? So, okay, when it comes to absolute values, anytime in math you're dealing with an absolute value, there's typically going to be one of two avenues that you'll need to take to analyze the problem. The first thing you want to look for is, so look at the constraints of the problem and see if for whatever you're analyzing, maybe you're analyzing a limit as x approaches a certain number, or maybe you're taking the derivative at a certain value, or whatever the case may be. It might be that since you're only dealing with a certain portion of the real number line, so here's all real numbers, here's the origin. If you're strictly in the positive region of the real number line, then you can simplify the absolute value, because if you know that whatever the expression is inside of the absolute value is always going to be greater than 0, well, then you could just remove the absolute value. Or if you know that, and in this case, it's just whether or not we're on the left or the right side of 0, but depending on the expression inside the absolute value, it might be that the crossover point where the expression inside the absolute value crosses over from positive to negative might be like here at -7 or something. But if you know, based on the constraints of the problem, that no matter what x you plug in, right, thinking about like a limit, the limit as x approaches a of some function with an absolute value in it, well, if you're only going to be right around a, above or below a, and that means that the expression inside the absolute value is always going to come out to be a negative value or always a positive value, then you can simplify the absolute value. If you know that the expression inside the absolute value is always going to be negative, well, you just remove the absolute value and put it negative. Okay, now, but in this case, for this problem, we don't have any constraints. They're just asking us in complete general, the f of x is equal to the absolute value of x. Where is it differentiable and not differentiable? So there's no constraints here. We can't simplify this absolute value. So what do? Well, this is the other avenue that you'll typically go down when dealing with absolute values. So you just break it up into two separate problems is all. You break it up into a problem where, okay, if x is greater than or equal to 0 in this case, this is going to be positive or 0. And then, okay, now the second case is what about when x is less than 0? You just analyze the problem from two separate perspectives and then compare those perspectives. So, okay, if x is greater than or equal to 0, then we know that we're dealing with f of x is equal to x. Because if the x we're inputting into this function here is always greater than or equal to 0, then you don't need the absolute value. Now, if x is less than 0, then we're dealing with f of x is equal to minus x. Because, like, okay, you input -3 into this function, but now what you want then, the output is +3. So if anytime we input something that's less than 0 here, just multiply by -1 to get the output of the function. Okay, and so now what we can do is, let's start by ignoring the crossover point, the x is equal to 0 point, because that's a little bit tricky. We'll analyze the crossover point last. So let's change this here to just x being greater than 0. So now we're not dealing with the crossover point. And so what that means is that, so from the perspective of the derivative, the limit definition of the derivative, where x is approaching some limit point from both sides of the limit point, we can think about applying that limit definition on the open interval here from 0 to infinity. And here on the open interval from -infinity to 0. Because we can get infinitesimally close to 0 here from the right of 0. And as we're doing that, we're still applying the limit definition of the derivative, right? Because like if we said this was a closed interval, then we can't really apply the limit definition of the derivative because we can't approach 0 from the left. But if this is open, then we're never actually going to be applying the limit of the derivative at exactly 0. So, okay, if we think about the graphs of, so we've got y is equal to x, and y is equal to minus x. Our intuition tells us that for these x values, x is greater than 0, x is less than 0, this function, the absolute value of x, is differentiable everywhere, because at any point, at any x input, for either of these lines, you're going to have a corresponding slope value, because at any input, for any x that you input into the function in these regions, there's going to be a tangent line to the curve, a clear tangent line to the curve with a clear slope. Okay, but now we need to officially prove this. Our intuition tells us this is true, but we need to officially prove it. And we can do that using the definition of the derivative. So, okay, so they use the limit as h approaches 0 of f of x plus h minus f of x over h, that form of the derivative. And so here, when x is greater than 0, you could just remove the absolute value. And so when x is greater than 0, f prime of x is equal to this limit here. The x's subtract out, the h's cancel, and the limit is equal to 1. So when x is greater than 0, the derivative of f prime of x for all x, for any x that's greater than 0 that you would plug into the derivative function, like what it's saying is that, so f prime of x is equal to 1. F of x is equal to the absolute value of x. F prime of x is equal to 1 when x is greater than 0. It's a constant value, and that makes sense because it's a line. A line has the exact same slope of the tangent line to the curve everywhere. The slope of a line doesn't change. It's constant. And so, okay, f of x is differentiable for all x is greater than 0 because you plug any x that's greater than 0 into the derivative function, you get an output, 1. All right, what about when x is less than 0? So now they apply the same limit here, but to simplify the absolute value, you remove the absolute value and put a minus sign out front, and you get f prime of x is equal to minus 1 for all x is less than 0, and this makes sense as well. So when x is greater than 0, the function is the line f of x is equal to x, which has this constant slope of 1 everywhere. And same idea when f of x is equal to minus x. You have this exact same slope of the tangent line everywhere that's equal to minus 1. Okay, so the function is differentiable for all x greater than 0 and less than 0. And the reason is because if you plug any x that's greater than or less than 0 into the derivative function for this function, you're going to get an output. So now what about when x is equal to 0? Well, okay, to determine if the function is differentiable at x is equal to 0, we know that the definition of differentiability is that the derivative exists. The limit definition of the derivative exists. The limit as h approaches 0 of f of x plus h minus f of x over h exists. Well, we know that one way we can check to see if a general two-sided limit exists and what it's equal to is by evaluating both of the one-sided limits. So looking at the limit as h approaches 0 from the left of the function, as well as the limit as h approaches 0 from the right of the limit function. And if those two limits are equal, then that proves that the general limit exists, and whatever that they're equal to is what the limit is equal to. So, well, we know we can evaluate if the limit as h approaches 0 from the right means that the argument inside the absolute value is always positive because you're always to the right of 0. So we can simplify for that one-sided limit. We can simplify the difference quotient. Just remove the absolute values. So the limit as h approaches 0 from the right is going to be 1. It's going to simplify to this form here, and then to h over h. So the limit as h approaches 0 from the right is equal to 1. And same idea as far as the limit as h approaches 0 from the left. Well, the x is always negative, so the limit as h approaches 0 from the left is going to simplify just like it did here. You remove the absolute values, put a negative sign out front, and you're left with minus 1. So the limit as h approaches 0 from the right is 1. The limit as h approaches 0 from the left is minus 1. So there you go. The limit as h approaches 0 in general doesn't exist. This here, when x is equal to 0, this limit doesn't exist, which means that the function is not differentiable at x is equal to 0. So it's the answer to this question is that the function is differentiable everywhere except at x is equal to 0. And we can think about what's going on here if we look at the graph, the general graph of the absolute value. So it's interesting, if you recall, in general, absolute values are continuous at their crossover points. You can draw an absolute value in general. I mean, it depends on what exactly is inside of the absolute value, what expression, but in general, you can draw an absolute value through the crossover point without picking up your pen off the page. Okay, but what happens, though, the majority of the time at the crossover point, what you end up having is it's not smooth. We talked about how a function can be, over intervals, can be continuous and smooth. Like, that's two separate properties. Is a function continuous over an interval or at a point, or is a function smooth over an interval or at a point? And smoothness is in reference to differentiability. If a function is differentiable at a point or over an interval, then you're saying that the function is smooth over that interval. There's no sharp point or kink. And the issue when it comes to differentiability with a sharp point or a kink is that what you have is two separate slopes, that depending on if you're approaching the kink point from the left or from the right. So if we're approaching, just strictly looking at this absolute value from the right side of the crossover point, well, then the slope is this positive 1, right? But if we're looking at the crossover point from the left side of the crossover point, well, then the slope is negative 1. That's always going to be the case when you've got some continuous point on a curve, but that point is a sharp point or a kink. In those cases, the reason why the function isn't differentiable at that point is because the derivative, the limit definition of the derivative, if you do a one-sided limit, derivative limit, you're going to get two separate values approaching that point from either side. But it is interesting, though, you can see that there is some usefulness to analyzing the derivative at a point, but just from one side. I mean, it's still useful information if you've got some kink in a graph, right? Well, it's useful. You can determine that the function is continuous here, but then, okay, so it's not differentiable, but you might want to analyze, well, what's the slope as the function approaches this point from the left? And then what's the slope as the function approaches this point from the right? And you can note that information. Still useful information, right? But like, as opposed to a polynomial, any polynomial which is smooth and continuous everywhere in its domain. So any point that's obviously continuous, you can draw the entire function without picking up the page, but at any point, approaching that point from the left or from the right, you have the exact same tangent line. You see? Which is why it's differentiable. Okay, and so, therefore, if we plot the f prime of x, so here's f of x, the absolute value of x. If we plot f prime of x, it's just going to be, when x is less than 0, it's just minus 1. When x is greater than 0, it's 1. But then at x is equal to 0, the function doesn't exist. There's no closed circle anywhere. So the resulting f prime of x, it has a jump discontinuity at x is equal to 0. In particular, a jump discontinuity to where the function isn't defined at the discontinuity. Okay, so it says both continuity and differentiability are desirable properties for a function to have. The following theorem shows how these properties are related. So if a function is differentiable at a point, then the function must also be continuous at that point. Interesting. If a function is differentiable at a, then the function it must be continuous at a. That must be the case. So they go through an official proof of this theorem on the next page, but we can sort of unofficially break this down here intuitively. So we know that the meaning of continuity, for a function to be continuous at a point A, there's 3 criteria. So first, the limit as x approaches A of the function needs to exist. So it's going to be equal. So if it exists, it's equal to some value L. Second, the function evaluated at A needs to exist. The function needs to exist at A. It needs to be equal to something at A. Okay, and then third, L is equal to G. The limit of the function as x approaches A is equal to what the function evaluates to at A. So let's intuitively think about why it's the case that if a function is differentiable at A, then it must be the case that it's also continuous at A. Well, okay, we could think about how there's no way a function could be differentiable at a point if the function itself doesn't even exist at that point. How could there be a tangent line to a curve at a point if there's no curve? So if a function is differentiable, then automatically this is satisfied. Easy. Okay, so now it's tempting to say that criteria 1 is automatically satisfied because, well, if the limit as x approaches A, the function doesn't exist, then the derivative won't exist either. The limit of the derivative won't exist. But this is a little bit different because this is f of x. This is the limit as x per se of f of x, not the difference quotient. Okay, but if we think about the meaning of continuity from a graphical standpoint, okay, so we've established that the function needs to exist for sure. Okay, so we're going to have some dot here, some closed circle somewhere here at x is equal to a. Now, but if the limit exists, but let's say a is, the limit L is not equal to what the function evaluates to at a. So this is L, and then this is G. Well, okay, again, this isn't an official proof. This isn't an official math proof, but once again, this is similar to the idea of the function not even existing, in the sense that there's no point here for a tangent line. Yes, the function exists, but where does the tangent line go? You could say it can't go here because the tangent line isn't touching the curve. There is no curve here at x is equal to a. You might say, well, okay, what about up here? Well, no, because a tangent line is a slope. You need the whole idea of, like, this is point P and point Q is some point off of point P, and you're taking the limit as Q approaches P. Well, you can't do that here. So this scenario is similar to saying that the function, in a sense, still doesn't even exist here from the perspective of the slope of a tangent line. Okay, so now, but here the limit exists, but G isn't equal to L. You could have a case where the limit doesn't even exist. So this is G, and there is no L, the limit doesn't even exist, but the derivative limit approaching a from one side does exist and is equal to G, but in general from both sides, the derivative won't exist. And then for like an infinite or an oscillating discontinuity, you could think about how the limit derivative isn't going to exist from the perspective of that. So in this case, the limit derivative exists from either side, but it's just not the same, approaching the same value from either side. But with an infinite or an oscillating discontinuity, even the one-sided limits for the derivative wouldn't exist. You would never be settling in on some finite value. So it makes intuitive sense that there's no discontinuity to where you could have a function be differentiable at a discontinuity. Okay. So here they go through the proof of this theorem. We're not going to look at the proof. Now it says here that, note that the converse of this theorem 4 is false. That is, there are functions that are continuous but not differentiable. So it's not the case that if a function is continuous at a point, then it must be differentiable. And we just saw that with the absolute value. The absolute value of x is continuous through this kink point, but it's not differentiable. Or a function like this is continuous here, but it's not differentiable. So it's only the case that if a function is differentiable at a point, then it must be continuous at that point. Okay, so how can a function fail to be differentiable? We saw that the function y is equal to the absolute value of x is not differentiable at 0, and the graph of the absolute value shows that its graph changes direction abruptly when x is equal to 0. In general, if the graph of a function f has a corner or kink in it, then the graph of f has no tangent at this point, and f is not differentiable there. Yeah, this is everything we just talked about. So how can a function fail to be differentiable? The first rule is the function continuous at that point? So when we're asking this question, how can a function fail to be differentiable? Remember, we're talking about a point at a time. This is a point-wise property. You can think about an interval, but when you're thinking about an interval, you're thinking about all points within that interval. So specifically here, we're asking, how can a function fail to be differentiable at a point? The first question is the function continuous at that point? That's going to take care of, does the function exist? Right? It doesn't make sense to think about differentiability at a point if the function doesn't even exist at that point, but it's more than that. It needs to be continuous. You can't have a function exist at a point but have something like this. So the first question you ask is the function continuous at that point? If you've established that the function is continuous, then the next question you're asking is, okay, well, is that point some sort of a corner or a kink? Like the absolute value. It's like a corner here or a kink. And if you have a corner or a kink, the function is not going to be differentiable because of everything we just talked about. It's because the derivative approaching from that corner or kink from the right and the left aren't the same. But a corner or kink has more of a derivative characteristic than does a discontinuity, because at least in the case of a corner or a kink, you do have a slope here. So there, as the derivative approaching the kink here from the right, there is a slope, right? And same idea coming from the left. So there is more of a derivative characteristic to corners or kinks than there are discontinuities. But still, technically, the general derivative does not exist. It's not a function is not differentiable at a corner or a kink. Okay, theorem 4 gives another way for a function not to have a derivative. It says that if the function is not continuous at a, then the function is not differentiable at a. So at any discontinuity, for instance, a jump discontinuity, the function fails to be differentiable. Yeah, this is everything we just talked about. Okay, now a third possibility is that the curve has a vertical tangent line when x is equal to a. That is, the function is continuous at a, and so, yeah, we haven't talked about this yet, so you could have a case like this, where so let's say you have like a corner here, something like this. And so what's unique here, the function is still not differentiable here, but what's unique is that what you would find is when you apply the derivative approaching this point from the right, the limit is going to not exist. So the function isn't differentiable. However, it's going to be an infinite limit. The limit, the derivative limit is going to approach infinity. And actually, in this case, it would approach positive infinity coming from the left. It would approach a vertical line coming from the right, and then it would approach negative infinity, a negatively sloped vertical line coming from the left. So that's why they have the limit as exponential of the absolute value of f prime is equal to infinity. But we could think about a true vertical tangent in which the general limit from both sides would be the same infinity if you had something like this. So here, the function isn't differentiable here if this is truly gone vertical. And the reason is because you take the limit as x approaches. If it hasn't truly gone vertical, then this is differentiable. But if this is really a vertical tangent here, then the limit for the derivative approaching this point A from the right is equal to infinity, and from the left it's equal to infinity. The limit's going to go to infinity. So in that case, you'd have a true vertical tangent, in which case the limit as exponential of just the derivative is equal to infinity, not the absolute value. So this is another way that, again, the function is not differentiable at these vertical tangents when the derivative goes to infinity, because an infinite limit doesn't exist, right? But it's a unique type of non-existence, a vertical tangent. Where again, in this case here with the absolute value, that they're using this absolute value because at a kink like this, as the limit of the derivative coming from the right is going to positive infinity, and then from the left it's going to negative infinity. So this means that the tangent line becomes steeper and steeper as x approaches a. Figure 6 shows one way that this can happen, and figure 7c shows another. So yeah, there's a true vertical tangent where you get an actual general infinite limit of the derivative. In this case, the limit as x approaches a of just the general derivative is just a d in e, because coming from the right you're approaching positive infinity, from the left negative infinity. But I mean, it's still actually, this is still the whole vertical tangent idea, whether or not it's positive or negative. A vertical tangent, whether or not the slope is a positive or negative slope, is still based on an infinite limit. So, okay. Now figure 7 shows the 3 possibilities that we have discussed. So yeah, here's a jump discontinuity. Here's a corner. All right. A graphing calculator or computer provides another way of looking at differentiability. If f is differentiable at a, then when we zoom in towards the point, the point of interest on the graph straightens out and appears more and more like a line. We saw a specific example of this in an earlier figure, in the precise definition of the derivative section. You really got a sense for the meaning of the slope of a tangent line to a curve if you zoom in extremely close to the graph of a function. Even if that function is very curved at that point, it's always going to come out to be, you're going to be approaching a straight line, like it's showing here. So you've got this curved parabola here, but if you zoom in closer and closer on a region, the graph visually starts approaching a straight line. If you kept zooming in, you couldn't visually tell that it wasn't a straight line. And that's the idea. That's what the slope of the tangent line to this point on the curve is approaching. But in the case of a sharp point or a kink, no matter how far you zoom in, you're still going to see that corner or kink. So that's a good illustration of differentiability. Okay, now higher derivatives. So if f is a differentiable function, then its derivative f prime is also a function. Yes. So f prime may have a derivative of its own. Yeah, any function of x we've just seen, you can take its derivative, right? So if a function f is differentiable and it has a derivative f prime, which we know is also a function, then perhaps f prime has a derivative. So we have f prime, we take the derivative of f prime, which is f double prime. This new function f double prime is called the second derivative of f because it is the derivative of f. Using Leibniz notation, we write the second derivative of y is equal to f of x as, so yeah, with Leibniz notation, which makes the meaning of the derivative very intuitive. So you've got dy over dx. Now, if we apply the derivative operator, this derivative operator to dy over dx, then we can write this as, so d squared y over dx squared, right? Because you have the two lowercase d's here, so d squared y, and then the two dx's, and you get dx squared. Now, this can get kind of confusing because you look at this notation and you think, well, all right, we know what dy and dx are. We talked about what dy and dx are, these infinitesimals, and the ratio dy over dx. Well, what is this? What is d squared y and dx squared? Are those infinitesimals like even smaller infinitesimals? Are you taking dy and squaring it? No. So d squared y and dx squared are mechanically, like physically, the exact same as dy and dx. This notation is just used to indicate its relation to a function that was 2 steps prior. At the end of the day, this is just a dy corresponding to f prime of x. So f prime of x is just some expression of x. It's just a function, like any other function. And we're just taking the derivative of that function, and we're going to get a dy over dx, an infinitesimal over an infinitesimal. So the resulting derivative of f prime of x is just like any other derivative that you can represent with an infinitesimal divided by an infinitesimal. However, if the context is such that a certain derivative that you're taking is a second derivative or a third derivative, then you're just going to use a different notation for those infinitesimals. That's it. So it's not like you're squaring dy here. So you have a small infinitesimal, and now you're squaring it and getting an even smaller infinitesimal. No, don't think of it that way. This is just the same exact type of infinitesimal, these two, as dy and dx are. It's just the context of these is different. The context of d squared y and dx squared is different from the context of dy and dx. Think of it like you've got the dy variable for this infinitesimal, the dx variable for this infinitesimal, but now within the same problem, since you're dealing with the same problem, you've got these new infinitesimals that you want to put a different label on them. Because this is a different infinitesimal than this infinitesimal, right? So this is just like a new variable for the same problem. This is d squared y, not dy. This is dx squared, not dx. Okay, so if f of x is equal to x cubed minus x, find and interpret the second derivative. So earlier we found the first derivative of this function to be 3x squared minus 1. So all we're going to do is just now take the derivative of this function. So they plug this function into the definition of the derivative. So here's f of x plus h. Then subtract from that f of x. Simplify the limit function. And you get, it simplifies to 6x plus 3h. So the limit as h approaches 0 is just 6x. And so now what they do here is they plot, here's the original function f, here's the first derivative of f, and here's the second derivative. It's just the line 6x, right? And so we know that f double prime is just the slope of f prime. So you're going to have f prime as a negative slope all the way up until x is equal to 0. So f double prime is below the x-axis. Then at x is equal to 0, you've got a valley here. It's a horizontal tangent line. So f double prime is equal to 0, which makes sense. And then as you continue past x is equal to 0, you have a positively sloped f prime. So now we're above the x-axis on f double prime. And what f double prime is telling us is that you have this constant change in slope of the parabola. So the slope of the parabola is always changing. You have, it gets, it's a steep negative slope here. Now the slope is shallowing out until the slope gets to 0, and then it's going past 0 with a positive slope, and it's getting steeper and steeper and steeper and steeper. But it's the change of the slope is happening at a constant rate. That's what the second derivative is telling us. And as far as what the second derivative is telling us about the original curve, it's describing the rate of change of the slope of the original curve in a similar way to how I just mentioned that the f double prime being a line means that the rate of change of the slope of this parabola is constant. Well, in that case, I'm describing the third derivative, because if you take the derivative of this line of f double prime, you're going to get a constant value, right? And that constant value is talking about how the rate of change of the slope, as you have a steep negative slope here, and then it increases at a constant rate to 0, and then continues to increase at a constant rate. That's what the third derivative would be describing. The third derivative is going to be, since this is a line, the third derivative is going to be just a constant value that's describing the rate of change of the slope of the second derivative. And so the second derivative is describing the rate of change of the slope of the original function. Okay, so if you find this confusing, like what exactly the second derivative is doing, what it means, don't worry about it too much at the moment. We're going to go into a lot more depth on what the second derivative means, the idea of the concavity of a curve. So it all comes down to the fact that you have a concave down curve in this region. And then when the second derivative switches from positive to negative, now we have a concave up curve. We're going to get into a lot more detail on the second derivative and concavity later in the course. So don't worry if you're a little bit confused. It's not a big deal. Okay, in general, we can interpret a second derivative as a rate of change of a rate of change. The most familiar example of this is acceleration, which we define as follows. So yeah, acceleration is a second derivative. You've got a position function. Okay, then if you take the derivative of a position function, you get a velocity function. If you take the derivative of a velocity function, you get an acceleration function, right? So very, very interesting, right? A of t is v prime of t. You take the derivative of the velocity, which is the second derivative of the position function. Acceleration is the change in velocity you feel when speeding up or slowing down in a car. Yeah. Okay, the third derivative, so I mean, you can theoretically take as many derivatives, there's like nth derivatives. There are certain functions we're going to learn to where they don't, like polynomials, if you keep taking derivatives of polynomials, they break down all the way till you get like a derivative equal to 0. But there's certain functions where if you keep taking the derivative of the function, it never breaks down, like e to the x or any kind of exponential, b to the power x. You can just take derivative after derivative after derivative, and it'll never disappear. So you can take like a 10th derivative, a 20th derivative, an nth derivative. So, but the third derivative is just, okay, you take the derivative of f double prime. So this is, you can interpret this as the slope of the curve of f double prime, or as the rate of change of f double prime. So we can apply Leibniz notation again. You have d squared y dx squared. Take the derivative of d squared y dx squared. You get d cubed y over dx cubed. And once again, don't confuse this and think that this is some, you're taking dy and cubing it. No, this is just the exact same as what we talked about as just an infinitesimal, like dy over dx, but they're just applying another variable to it because within the same problem, you're going to have multiple infinitesimals. There's a different context here for this infinitesimal. It's just like another variable applied to a different infinitesimal is all. This does not mean you're cubing an infinitesimal. All you've done here, fundamentally, all you've done is just you have some function of x. Y is equal to x cubed, or y is equal to the square root of x. But it just happens to be the case that in the context of a certain problem, this is a second derivative. I'm not putting the second derivative here to illustrate a point. It's just that in the context of a certain problem, in another problem, this might not be the case, but in the context of a certain problem, this happens to be a second derivative. So when you take its derivative and you get the dy over dx, which is just an infinitesimal like any other derivative infinitesimal, in that context, you're going to label these infinitesimals differently. You're going to say this is d cubed y over dx cubed. You're just going to put a different variable label to indicate where these infinitesimals are coming from. Okay. Now, we can also interpret the third derivative physically in the case of the position function. So if you take the third derivative of a position function, so the first derivative of a position function is velocity, second derivative acceleration, and the third derivative is what's called jerk, J. It's very interesting. That's the derivative of the acceleration function. It is aptly named because a large jerk means a sudden change in acceleration, which causes an abrupt movement in a vehicle. The differentiation process can be continued with the fourth derivative, the fifth derivative, etc., the nth derivative. And so in general, the notation for the nth derivative is this notation here and this notation here. You just apply the general n superscript where it's needed. Okay, so if here's the function x cubed minus x, now let's find the fourth derivative. So we found the second derivative in the previous example of x cubed minus x to be 6x. So we've got the line 6x. Okay, so what's the third derivative of x cubed minus x going to be? Well, what's the slope of this line? The slope of the tangent line to this curve is going to be the exact same slope everywhere. It's 6. So f triple prime of x is 6. The horizontal line y is equal to 6. Okay, what's the derivative of f triple prime? Well, it's 0. The slope of the tangent line to a horizontal line is 0 everywhere. So the fourth derivative of x cubed minus x is 0. Now, again, so you can see how with a polynomial like this, as you keep taking further and further derivatives, it's the function is like breaking down all the way to 0. But we're going to see other functions where that doesn't happen. You could take a trigonometric function, sine or cosine. You can take the 100th derivative of sine or cosine, and it's never going to break down. Okay, so we have seen that one application of second and third derivatives occurs in analyzing the motion of objects using acceleration and jerk. We will investigate another application of second derivatives in section 4.3, where we show how knowledge of f double prime gives us information about the shape of the graph of f. In chapter 11, we will see how second and higher derivatives enable us to represent functions as sums of infinite series. So yeah, if you feel like you don't have a full comprehension of exactly how the second derivative and the third derivative work and what they mean, don't worry about it. We're going to get into a lot more detail on the meaning of higher order derivatives as we continue in the course.